Okay, are we all ready to get started? Well, hello everybody. My name is Morgan Nasholds. I'm a physical scientist here at the U.S. Geological Survey, specifically with the GMEG Science Center here, mostly over in Building 3. Be louder. Oh, okay. Well, okay, I'll try to enunciate then. I'm Morgan Nasholds. I'm a physical scientist with the U.S. Geological Survey GMEG Center, predominantly based over in Building 3 over there. I will be talking to all of you about the volcanism of Arizona today. So Danny's talk was great. It was, and also quite serendipitous because it gave a good overview of geologic concepts. And with this, I'm going to get into the volcano basics, just to give all of you a good overview of what types of volcanoes we would be looking at across Arizona. So we're going to cover 5 volcano types here, and I do want to emphasize that there are more volcanic landforms than just this list, but for the purposes of this talk, I'm keeping to the ones that are relevant to Arizona. So as mentioned in Danny's talk, Mount Tambora is a stratovolcano or composite volcano, and usually they are formed of multiple types of lava overlapping, multiple different types of lava, like Danny pointed out, dacite, rhyolite, andesite, etc. One of the quintessential examples, other than Mount Tambora, of course, is Mount Rainier in Washington State. Typically, these are, as most people think volcanoes are, they're tall with steep slopes. They have these more explosive styles, although not all the time. They're formed of these more viscous or thicker lava types listed right there. And the types of eruptions that you see there can be both effusive, calm river flowing, or explosive. So this volcano section, this volcano basic section is going to have a little interactive section. I'm going to have an Arizona example over here, and if people would be so kind as to raise your hand and take a guess at Arizona's own stratovolcano or type of volcano that it's up on the slide. So let's get started. Does anyone want to take a guess or knows what Arizona's stratovolcano is? You are correct, the San Francisco Peaks, which is right behind us, albeit I'm not sure you can see it with all of the storms today. But yeah, so our own San Francisco Peaks, right above Flagstaff, are Arizona's version of a stratovolcano. The San Francisco Peaks were formed quite similarly to how Rainier and most other stratovolcanoes are formed, over about 500,000 to 1 million years of multiple different overlapping lava types, typically thicker, which leads to this more prominent, steeper landform. I'm also going to have an in-eruption slide because, I mean, we're talking about volcanoes. Let's keep the cool images up here. So this is Calbuco in Chile in 2015. This is a Plinian-style eruption where it's an explosive type of eruption that sends ash and rocks and gas high into the atmosphere, as you see right there. All right, moving on, we're going to go to shield volcanoes. So a quintessential shield volcano is Mauna Loa in Hawaii. For any of you who have been to the Big Island, usually the 2 big mounds that you see on the island are Mauna Kea and Mauna Loa. So shield volcanoes are typically lower elevation with gentle slopes. They're formed of less viscous or thinner lava types such as basalt, basaltic andesite, and sometimes andesite, albeit not terribly frequently. They have a very widespread surface area and form mainly through effusive activity. You know, perhaps for those of you who have witnessed volcanic eruption videos in the past, you see this classic lava fountaining and lava flows. That's the type of eruptive style that you will commonly see these volcanoes formed of. So this one's, as I go down this list, this is going to get progressively more and more perhaps esoteric knowledge in terms of, you know, Arizona's volcanoes. Does anyone know, so Arizona, to my knowledge, has 3 shield volcanoes. Does anyone want to take a guess at one of them? I do not see any hands. Oh. Unfortunately, Mount Eldon is not a shield volcano, but the one that I'm thinking of is Mount Baldy, all the way over in eastern Arizona by Springerville. It's very, as you can sort of notice from here, it has this widespread surface area, low slopes. Mount Baldy is a rather old shield volcano. Mauna Loa right here is still active. It's about 500,000 years old. Mount Baldy is in the range of millions and is no longer active. But regardless, it is a shield volcano. And also, just as a quick side fun fact, Arizona's 2 other shield volcanoes that I'm aware of are in the same field that Mount Baldy is in. In eruption, we have Kilauea, which is also on the Big Island. This is actually a picture that I took just about 3 weeks ago because I was vacationing on the Big Island, staying with my friend at the Volcano Observatory, and I was lucky enough to witness Kilauea's episode 32 of its current ongoing eruptions. But anyway, the classic type of eruption that you will see at these shield volcanoes is this fountaining with the subsequent lava flows that are coming out right here. All right, moving on, we are going to go to cinder cones, another very quintessential volcano type with its conical shape and relatively small form, and then the little spattering of the fire at the top. It's typically a pile of scoria or cinders, which is fragmented lava. Typically, cinder cones erupt similar compositions to shield volcanoes. They are less viscous lava types, such as basalt and basaltic andesite. In contrast to the previous 2 volcano types of stratovolcano and shield volcanoes, cinder volcanoes are usually monogenetic, which means they erupt only once. This is opposed to polygenetic, which means they erupt multiple times over their sort of eruptive lifespan, so to speak. So cinder cones erupt once and then they're done. This is the vent Komezuka, which is a sub-vent of Mount Aso, it's this greater volcano in Japan. So cinder cones are formed from a combination of effusive and explosive activity, usually accompanied by lava flows, which you will see there. So this was somewhat spoiled in Danny's talk, but it was still great. Does anyone want to take a guess at a cinder cone in Arizona? We have hundreds of them, so you can. Sunset Crater, everybody's, yeah. And so I put our favorite up there just because why not? So yeah, Sunset Crater is classic cinder cone that we all know and love. Other examples include SP Crater, Strawberry Crater, and actually a couple of the larger sort of cone-like volcanoes that you see to the west of Flagstaff. And in eruption, we have this picture of a vent of La Palma, Cumbre Vieja, which is the volcano on the island of La Palma in Spain. Erupting in 2021, this is the sort of classic eruption styles that we see at cinder cones. We see this explosive activity with a lava fountain on top, and then subsequent lava flows going down its flanks. Moving on to even more obscure volcano types, we have the MAR, M-A-A-R. These are usually very wide craters, have very low relief on the ground. So these are formed from very explosive activity. When you have magma intruding into any given surface, or any given portion of the crust, typically there are aquifers. There's even aquifers around here, despite how dry it seems. When magma intrudes into these aquifers, underground water reservoirs, it explodes because you have a material that is anywhere from 800 to 1,100 degrees Celsius interacting with water that is ambient air temperature at most, sometimes colder. So it explodes and it forms these massive craters. I should have put a scale on this, if anything. This is, I think Ukenrek Mar is about up to 1 kilometer, maybe 500 meters. They're very, very wide craters. Anyway, Mars are typically found in volcanic fields, but sometimes they can be found on the lower flanks of the strato or shield volcanoes as well. It really just takes magma intruding a water body. So again, back to the esoteric knowledge, does anybody have an example of a Mar in Arizona? I see a hand over there. Where? Dry Lake is correct. It's not the example I have up here, but that is a Mar. Here I have Rattlesnake Crater, which is similarly it's similarly within our Flagstaff area. I'm using a lot of Flagstaff examples here. Rattlesnake Crater is out to the west. So as you can see right here, it's not terribly visible in this image, but it's a very wide relief. This is taken from a scoria cone or a cinder cone that formed on the side of Rattlesnake Crater, but anyway, Rattlesnake Crater itself is a Mar. And in eruption, the last known eruption that at least I'm immediately aware of was indeed the Ukenrek Mar, or Mars. There's another one that erupted too, in 1977 up in Alaska. So as you can see, it typically has this distinctive explosive style. You can see the area around here is covered in ash. There was probably forest here once too, but when Mars open up, typically they send out these things called base surges, which are these very quick moving flows, similar to pyroclastic flows, except usually colder. But they are these rapidly moving clouds of ash and rock and sometimes gas, and sometimes they move at such speeds that frankly they act as not only sandblasters but just demolishers. So there may have been a forest around here, but when the Mars was opening up, it just kind of obliterated everything around it. Moving on, finally, we have the dome complexes or lava domes. It's somewhat semantics, but anyway, these are some of the steepest slopes of any active or recently dormant volcanic landform. I do want to make that distinction because there are volcanic landforms that can be long extinct that are way, way steeper, such as, say, Devil's Tower, or if any of you have been out to the Hopi Buttes, these are large eroded volcanic necks, but they are not erupting anymore. Anyway, so lava domes are some of the steepest of any active or recently dormant volcanic landform. These are typically made from viscous or thicker lavas. They cannot flow as far, so they don't end up forming things like shield volcanoes. So you end up getting something like this, which is one of the Inyo domes in California, just next to the Sierras. If any of you have never been to this region around Long Valley, I would highly recommend it. It's one of my favorite places in the United States. Anyway, so does anyone want to take a swing at Arizona's own examples? It was actually said earlier. Crystal. Mount Eldon is a lava dome or lava dome complex. You can see that you see these lobate features. They sort of look like the mountain is melting. So these are old lobes of, I think, dacite lava. So it's very viscous. It does not flow very far. Lava domes, when they form, they're mostly effusive, but they have a few smaller explosions or collapses. The in-eruption example I chose is Volcán Chaitén, which erupted in Chile in 2008. This is what a lava dome looks like when it is erupting. It's this gigantic steaming mountain. Every so often you have these explosions either at the top or because frankly it's so steep it goes over the angle of repose and all of this frankly hot, still fresh lava, I think dacite or rhyolite in this case, collapses down the flanks and forms these pyroclastic flows, which are these billowing clouds of exceedingly hot gas and ash and rock. So Mount Eldon would have done that too. In fact, I think there are some deposits that can be found on the eastern side of Flagstaff that retain this record, showing that Mount Eldon did have a little bit of explosive activity. Not the same level that I showed you in the stratovolcano, not like gigantic towering column of ash and gas, but still little explosions that could be probably seen locally. All right, so with the volcano basics in our arsenal, we can move on to Arizona's volcanoes. So I'm going to be covering the ones that erupted in the Quaternary period, so under 2.58 million years ago. So there are 7 volcanic fields within Arizona that have been active within the Quaternary period, so from 2.58 million years ago until the present. 2 of these have produced eruptions in the Holocene epoch, which is defined as about 11,700 years ago until the present. We are currently in the Holocene epoch. And the types include cinder cones, Mars, dome complexes, strato, and shield volcanoes. This is a map that I have modified from our colleagues at the Arizona Geologic Survey. This is their map. I made a little change here where I put the changes to SF, meaning San Francisco. So the 7 volcanic fields I will be discussing in this talk are the Uinkaret volcanic field up here north of the Grand Canyon, our beloved San Francisco volcanic field, which we are actively within and surrounds us, the Springerville volcanic field out in eastern Arizona, the San Carlos volcanic field down in east central Arizona, the Sentinel volcanic field, Pinacate volcanic field, and finally the San Bernardino/Geronimo volcanic field all in southern Arizona. So the most recent eruption in Arizona was approximately 940 years ago, 1085 CE, and it was at our beloved Sunset Crater. Now you might be wondering, because in Dan's talk, he taught all of you about the Ring of Fire and subduction processes. So you might be wondering, well, is there any subduction going on beneath Arizona? There is not. So then you might respond, well, why are volcanoes erupting in Arizona? And so the reason is twofold. It's thought to be due to 2 ongoing current geologic processes. So the first being a difference in crust thickness at the edge of the Colorado Plateau. So this is the Colorado Plateau. It's this region of broadly much thicker crust, and it obviously does not just take up northern Arizona. It kind of extends all the way. If you all could imagine a map of the United States, it extends quite a bit farther. Anyway, it's a very thick chunk of crust. And then right here, you have much thinner crust in the Basin and Range, or as the map states, Range and Basin province. So the difference in crust thicknesses leads to this purple-ish, pale purple zone called the transition zone. And this creates tiny instabilities at the edge of this thicker crust that can help enhance magma production at the crust mantle boundary. And so essentially you have some of this hot material rising as convection dictates it do. It erodes slightly at the edge of the Colorado Plateau, and then you have little pockets of magma that make their way up and end up forming these broader volcanic fields. I would argue that that ongoing geologic process is predominantly what influences the 4 volcanic fields up here, Uinkaret, San Francisco, Springerville, and San Carlos. Whereas in the southern portion, we have Basin and Range extension. So the crust is steadily pulling apart. It's not going to just break apart in our lifetimes, don't worry. This is occurring over geologic time, so we cannot see it happen. But anyway, the crust is slowly pulling apart, and as it does so, of course, it fractures and breaks, and magma intrudes and exploits some of these weakness zones in order to erupt to the surface, producing the 3 southern, younger volcanic fields in Arizona. And so volcanoes in Arizona have had a very distinctive influence on the human history and, of course, the geography of the state. Without volcanism in Arizona, we would not have one of Arizona's most prominent landmarks and also tallest peaks, the San Francisco peaks and Humphreys Peak. You know, the Uinkaret volcanic field, as I will delve into in its main slide, has had a very distinctive influence on the Grand Canyon and the Colorado River. And of course, the human history, I'll have a slide about that later, but indigenous populations witnessed 2 eruptions in Arizona and potentially a 3rd one, but I'll get to that later. Broadly speaking, eruptions in Arizona are, especially compared to Mount Tambora, much, much smaller and much, much more localized, and to my knowledge have not killed anybody. So you don't need to worry too much about it. The state will see another eruption in the likely far future, and when I say far future right here, I'm referring to sort of our human timescales. So, you know, likely long after all of us are gone, but in the geologic time span, probably very shortly. So, you know, the last one being 940 years ago at sunset. On average, I mean, average rates are average rates are average rates. You can see that I have some thoughts about that, but essentially the average frequency of eruptions in Arizona or the broader southwestern United States is between 2,000 to 3,000 years. So unfortunately, we won't see another sunset, at least going off of that metric, for another 2,000 years. Anyway, they're small and localized eruptions. They're not these very large and sort of, you know, catastrophic eruptions. Locally, they're catastrophic, but just not regionally or globally. All right. Oh, I went back. Okay, so we're going to start with the San Francisco volcanic field, and I'm going to briefly transition to Google Earth to help me in this journey, to help introduce all of you to this and see if my mouse works. Okay, cool. So this is our beloved state of Arizona. I have the 7 volcanic fields I'll be talking about highlighted here. So we're going to zoom into the San Francisco volcanic field and then briefly go back to the slide. There we go. So at about 4,700 square kilometers, and the mileage conversion is right there, it is the largest volcanic field in, I believe, the Southwest in general, and potentially the entire contiguous United States. Its overall age is 6 million years, being the oldest out west and then youngest moving towards the east. Its last eruption, of course, was at Sunset Crater. The volcano types that we see here are stratovolcanoes, such as the San Francisco Peaks. This is a picture that I took of the eastern field from the top of Humphreys. Cinder cones like Strawberry Crater and Sunset Crater and SP and about 400 others. Mars, such as Rattlesnake Crater, and I'm not really sure of any others. And then lava domes such as Mount Eldon, or also the Dry Lake Hills, which is this small little band of hills that you see to our north, typically in front of the peak. And so every slide I'm going to have a little neat volcano fact, neat being somewhat subjective, but in my opinion it's neat. The San Francisco volcanic field has the broadest variety of lava types and volcanic landforms in the entire state and perhaps the entire southwestern US. It has everything from basalt all the way to rhyolite. Basalt, an example would be Sunset Crater. Rhyolite would be Sugarloaf Mountain. For those of you that have ever tried to hike into the inner basin, Sugarloaf Mountain is this big lava dome, actually. It's made of rhyolite, which is the thickest lava type. So I'm just going to have a little portion where I zoom into the youngest eruption here, which will be Sunset Crater. So this is Sunset. I don't really have much else to say. I just figured I'd zoom around because it's cool. Yeah, you can see it right there, and then we have the San Francisco peaks. All right, so actually I'm going to stay here, and the next field we're going to slide to is the Uinkaret volcanic field, which lies in the northwestern portion of the state. So let's see. How many of you can guess what this gigantic landform on the satellite is? It's the canyon. You're correct. The Grand Canyon, our favorite landform in the state. So let's see. Oh, actually, sorry. Briefly going back to the San Francisco volcanic field because I forgot I had these extra 2 slides. Here's SP Crater, north of the peaks, and here's Colton Crater and Kendrick Peak in the background. Kendrick Peak is another lava dome. I do quickly want to mention, again, with the San Francisco volcanic field, it has one of the smallest cinder cones I've ever seen. And the reason I say this is because sometimes when I'm bored, I browse Google Earth and look at volcanoes for fun, because I'm a volcanologist, and what else would I do? Now, this little crater, this little cinder cone that I've seen inside Colton Crater is genuinely one of the smallest cinder cones I've seen browsing the entire world. The only other one that matches it is a volcano in El Salvador, which also has a very tiny cinder cone in its crater. Okay, so now we're going to move on to the Uinkaret volcanic field. I do want to point out this quote by the USGS founder, J.W. Powell. What a conflict of water and fire there must have been here. Just imagine a river of molten rock running down a river of molten snow. The river of molten snow he's referring to is the Colorado River, as it's predominantly fed by snow runoff from the Colorado Plateau. So the Uinkaret is quite a bit smaller and quite a bit younger than the San Francisco volcanic field at only 3.6 million years approximately. Now, its last eruption was about 975 years ago at the Little Springs lava flow, which I will zoom into right here. It's kind of smack dab in the center of the volcanic field. You can see it looks quite a bit fresher, quite a bit darker in satellite imagery than the surrounding forest overgrown place. The cone was a cinder cone, but it kind of rifted in 2 and had lava flows flow out either side. Sometimes cinder cones are destroyed by the lava flows that come up from beneath them. So the predominant volcano type within the Uinkaret field is pretty much only cinder cones. As we zoom out here, you'll see a lot of these sort of cone-like features that, say there. You actually have a few down here. That's Vulcan's Throne, for those of you that have ever rafted the Grand Canyon. Exceedingly impressive spectacle, I shall say. There's more of the cinder cones that go over there, but broadly speaking, it's all just cinder cones. Now, the neat volcano fact is that the Uinkaret volcanic field has produced fissure vents and cinder cones which have erupted either directly within the Grand Canyon or have flowed into the canyon, as you see very prominently in this helicopter footage and in this Google Earth image that I took. Many flows that didn't erupt in the canyon flowed directly into it, and in some cases, you even had volcanoes that formed across the canyon from the main Uinkaret field. And I just want to quickly point that out. This is the main field over here, but if you zoom in right here, these 2 darker cones are old cinder cones, and they erupted literally on the other side of the canyon. The shadows here are kind of obscuring it, but there are actual ancient fissures that one can see, indicating that at some point in time, if you were lucky enough, you could have looked down into the canyon, and instead of seeing the Colorado River, you'd see a fountain of lava. Now, when this happens, it commonly dams the Colorado River because there's not very much area to fill up there. And these, they're typically quite voluminous lava flows. And so these form these dams, which end up creating these rather large lakes that fill up the better part of the canyon. Eventually, these dams catastrophically fail and cause large floods downstream. All right, next field up is the Springerville volcanic field. We're going to jump back to Google Earth here and zoom over to the Springerville, which is in eastern Arizona, named after the town of Springerville, which I think is right there. Yeah, so the Springerville volcanic field is quite similar to the San Francisco volcanic field. It has these broader, lower landforms. You know, if I kind of zoom to a more horizontal view here, you don't see any prominent San Francisco peaks here. Mount Baldy, which is the shield volcano that I pointed out, is right there. A lot of these are just all old cinder cones. So let's see, going back to it. It is the oldest dated currently field in Arizona at 7.6 million years. Its last eruption potentially was 300,000 years ago at Cerro Hueco, which I have also marked here. We're going to briefly zoom over to it. Cerro Hueco, I believe, is a maar, just based on its general structure. So right there you see a cinder cone, potentially another cinder cone, but then you see this very deep crater with very low relief on the land. In fact, it looks flat, but there's a giant crater there. So that's Cerro Hueco. So the predominant volcanic landforms you see there are shield volcanoes in the form of Mount Baldy and two others, I think Turkey Mountain and Coyote Hills. They're much smaller shield volcanoes. Cinder cones, of course, and maars, potentially in the case of Cerro Hueco. Its neat volcano fact is that it's neck and neck with our own San Francisco volcanic field as one of the most extensive and longest lived distributed volcanic fields in the entire United States. Our next one will be the San Carlos field, which is in eastern central Arizona, demarcated by these kind of patchy red blobs here, which are all the ancient lava flows that have been mapped. So it's a rather small field coming in at only 1,100 square kilometers. Its age is, it's had eruptions approximately between 4.2 million years and the last one being potentially 500,000 years ago. Please note the question mark there for later in the talk. Its predominant volcano types are cinder cones and associated lava flows. We can briefly zoom into a relatively good example here. Now, you can see the sheer amount of erosion that's taken place. This is a crater. Doesn't really look like it, but it's eroded, and it's had a massive lava flow come out of it since then. So the fun fact here is that the San Carlos field has incredible examples of mantle xenoliths, which are these crystals and this rock sample that you have on the right here. So mantle xenoliths are crystals, minerals of olivine that form directly in the mantle, and then when magma rises through these when magma rises through the mantle and crust, it takes up some of these xenoliths that are forming. It kind of tears them up in the conduit that is having magma rise through it and erupting to the surface. So essentially, if you ever get to behold a mantle xenolith or physically hold one, you are essentially holding one of the deepest samples that a human can really attain from the Earth, because it's coming directly from the top of the mantle, which is quite deep, tens of kilometers, tens of miles into the Earth. I don't think we can even drill that deep. So, you know, pretty darn good example here. So the next field, is the San Bernardino or Geronimo volcanic field. It kind of seems to have two names based on the limited studies that exist for it. It's located in the far southeastern portion of Arizona. In fact, just zooming out briefly here, we have New Mexico, and then we have Mexico down here. So, and then that's the state line with Arizona. It's not very visible, but just take my word for it. There's the San Bernardino / Geronimo volcanic field. All right, so just slightly larger than the San Carlos volcanic field. It is about 3.2 to potentially 270,000 years ago, being the youngest dated, again, question mark. Its predominant volcano types are cinder cones and the most maars that I have seen in Arizona. So both these pictures are of Paramore crater that's in the center right here with a perennial lake, and then this is taken from inside of the crater. its neat volcano fact is that I believe that Paramore Crater is the deepest maar in Arizona. It clocks in at just over 100 meters or 300 feet deep. Forms this very big bowl-shaped depression in the land. And I'm going to zoom into it right here. It's quite prominent on Google Earth. A lot of the pictures, well, of the few pictures I've seen of this field, it looks quite nice. Just, I don't know. Looks nice to do field work in. All right. So now we're going to move to a couple slightly more obscure volcanic fields, at least as far as Arizona is concerned. We have the Sentinel volcanic field, which is located over in the Mojave Desert region. So for those of you, if any, coming from the Phoenix metropolitan area, that is Phoenix right there. So the Sentinel volcanic field is located here. It clocks in at about 3.3 to 1.3 million years in terms of its total lifespan. It's predominantly formed of cinder cones and shield volcanoes, and is a good example of plains-style volcanism. Now, plains-style volcanism was first defined up in Idaho. If any of you have been to Boise, you'll notice that it's quite flat around there. The most prominent landforms that you'll see between the two mountain ranges are these low shield-looking things. So those are small shield volcanoes. Now, plain-style volcanism is where you have the formation of a lot of these things over a broad area. And so the Sentinel volcanic field checks that list. I believe one of the shield volcanoes is right here. It's not very visible even on satellite imagery. It's a very eroded field, you know. Its last eruption was 1.3 million years ago. So the next one that I'll be moving on to, and the final one, is the Pinacate volcanic field. Now, the Pinacate volcanic field has a very limited distribution, seemingly, but that's not just the field. This is the Pinacate volcanic field. The reason that it ends there is because this was a geologic map of Arizona, not Mexico. So anyway, this is the Pinacate volcanic field. So it's a volcanic field shared by both Mexico and Arizona. Its age is approximately up to 2 to 3 million years, and its last eruption, although to my understanding, especially because I know somebody who works on the Pinacate volcanic field, this is controversial. It's thought to have potentially erupted within the Holocene, as there are regional indigenous oral histories of eruptions happening in the region. So the predominant volcano types that we see are the shield volcano, is one shield volcano, which is Santa Clara Mountain. It's this rather broad edifice that you see right here, with many little cinder cones on top of it. Many other cinder cones and maars, such as this very beautiful maar right here called Cerro Colorado. And these darker flows right here are thought to be one of the more recent eruptions, potentially 12,000 years ago, but like I said, it's a ongoing topic of research as to when that actually happened. So it's predominantly located within Mexico, shares some of its volcanic distribution with Arizona, but it's associated with the gradual opening of the Gulf of California rift zone, which is this entire region. So this is Baja California, Mexico, Arizona, and California up here. This entire region is steadily rifting as the plate is being dragged north by the San Andreas Fault Zone, which goes approximately through here. And as it rifts, again, the crust is steadily pulling apart. And so we have magma intruding areas like that. You actually have a couple small volcanoes up here and further north, but the Pinacate volcanic field is essentially the first superficial above water expression of volcanism due to this ongoing process. All right, so moving on to Arizona's volcanoes and humans, or as I like to call it, its anthropovolcanological history. You could also switch it around and call it its volcano-anthropological history, regardless. So the two main instances I'm going to cover here are in our own San Francisco volcanic field and then in the Uinkaret volcanic field. So the eruption of Sunset Crater displaced a portion of indigenous Sinawa or ancestral Puebloan people. Now, previously, Walnut Canyon and Wupatki settlements did have some pre-eruption populations, but they were relatively small. Now, when Sunset Crater displaced the portion of Sinawa people that were originally where it erupted, many of them headed over to Wupatki. We see some very impressive archaeological evidence of maize impressions, corn impressions, on basaltic lava from the Sunset Crater eruption. I have to give the indigenous people who did this credit, because I have approached an active lava flow, and being 1,100 degrees Celsius, even with a thick leather glove designed to protect myself, I still singed some arm hairs. So I'm sure that they had protection of their own, but regardless, approaching a flow like this, especially to put corn into it or to put objects into it and then retrieve those objects, is brave. So the lavas from the San Francisco volcanic field and other volcanic fields, but we're focusing on San Francisco here, were used for multiple purposes. So for those of you who like to cook, mortar and pestles, good for grinding spices and whatnot, basalt is great as a mortar and pestle. So some indigenous people use that for grinding tools. Sharper lava rocks are good for leather work, taking the fur and all the other refuse off of an animal hide. And then the various colorations, predominantly red and black and gray, that you find around Sunset Crater can be used in pigments. So artwork, ceremonial purposes, etc. Agriculturally speaking, growing fields on a region that has been covered by a bit of volcanic tephra is beneficial, at least it's thought, for a few decades afterwards, after which it loses the water retention that some of the volcanic tephra brings. So it's thought that some people migrated back to within the Sunset Crater region, probably not next to the cone, but within it where there was much tephra fall, and actually grew relatively, basically improved their agriculture, at least for decades, because it retains water better. So I would recommend a reading here, Talking with Volcano Native American Perspectives on the Eruption of Sunset Crater. It's a joint work by people from University of Arizona, Northern Arizona University, and then Navajo and a few other indigenous tribes around here, talking about their oral history and relationship to Sunset Crater. When Sunset Crater erupted, it wasn't just the Sinawa people who it displaced who saw it. You could see the Sunset Crater eruption probably from a better portion of Arizona. Maybe not Phoenix, potentially, but you would have seen it for many, many, many miles around. So many indigenous people had interactions with this eruption. Moving on to the Uinkaret volcanic field north of the canyon, historically, the Southern Paiute people exist and still exist there. It's always been an important area for them, but the eruption of the Little Springs lava flow around 1075 AD became a significant cultural site. And this is prominently pointed out in my second recommended reading, which is the Little Springs Lava Flow Ethnographic Investigation. I don't speak Southern Paiute, so I don't want to potentially butcher the first part of that. But anyway, it's a fascinating investigation that incorporates many Southern Paiute people with Southern Paiute scientists, ethnographers, along with people from U of A and NAU, talking about their regional interactions with the Little Springs lava flow. Examples include sherd rocks, where there were fragments of pottery, again, placed on a portion of a lava flow, and then lava spattered onto it or destroyed the pot or did something, and then they went and retrieved these rocks that have these very distinctive pottery shards within them. All right, so I'm going to wrap up this talk with the idea that Arizona's volcanoes need more work. And this ends on a positive note. So if you've noticed, and I pointed out, many of Arizona's volcanic fields have these big question marks by their ages. These are not the only questions we have about Arizona's volcanoes. Much of the research over the last few decades, it's been great. It's been done by people from NAU, from the USGS, from the Arizona Geologic Survey, and it's predominantly focused on the San Francisco and Springerville volcanic fields. There have been a few other studies done for the others, but there yet remains a general lack of data, including the geochemistry, the geophysics, the geochronology, or the ages. We want to know when these things erupt, of course, the geologic mapping, and frankly, pictures for some of them. I had quite a bit of trouble finding pictures for some of the more obscure fields, like the Sentinel volcanic field or the San Bernardino volcanic field. So just to sort of drive that point through, I'm going to show a few examples of our state, which is broadly outlined in this square, and then different scale geologic maps that currently exist covering portions of our state. So this is 1 to 24,000 scale maps. This is 1 to 48,000 scale maps, and finally 1 to 100,000 scale maps. Some of them very well cover the Grand Canyon. That's what my group and I work on, and then covering the Phoenix metropolitan area and surrounding regions. And then I'm going to try and overlay some of the volcanic fields, which you'll see these big red blobs. And you'll notice that they don't overlap very frequently with any known geologic mapping in that area. Now, there are geologic maps that exist of these, but they were master's theses, and they occurred decades ago, and now we have improved methods to better understand these fields. So, let's see. Essentially, what this leads to is that there are quite a few unanswered questions about these distributed volcanic fields throughout Arizona and their implications for Arizona's future. Now, what I think this means is that opportunity abounds. Even though there has been decades of great geologic work, I don't want to discount that. There's been great geologic work done by the Arizona Geological Survey, Arizona State, University of Arizona, Northern Arizona University, and others, and then the USGS. There is still more work to be done. And with that, I'd like to thank you all for coming to this talk, and I will take your questions.